Dear AAAI researchers and fellow attendees, thank you for joining my presentation. First of all, I'd like to thank the committee for bringing together a multidisciplinary community advancing trustworthy AI in healthcare. My research toward preventive Alzheimer's risk screening with cell subtype aware brain-blood graph neural network aims to shift Alzheimer's detection from reactive diagnosis to proactive prevention, using NeoPlasmaNet, an interpretable AI system to detect molecular risk years before symptoms emerge through non-invasive AI-guided blood testing. Alzheimer's affects 1 in 9 seniors, and women are twice as likely to develop it. The disease begins decades before symptoms, but current diagnostics like PET scans and spinal taps are invasive and late stage, leaving 75% of at-risk individuals unscreened. Sex differences in hormones alter how brain cells handle stress and inflammation, so my research is sex stratified to uncover those early molecular patterns. I hypothesized that linking blood gene expression to cell type specific brain data can reveal sex-specific early Alzheimer's signatures before symptoms appear. To test this, I built an AI framework integrating single-cell brain transcriptomics with blood RNA data using biological pathways and known genes to guide model learning. Reliable AI begins with a clean dataset. I integrated single-cell brain transcriptomics, which is over 380,000 cells from the Cell by Gene Atlas, with blood RNA-seq datasets from Alzheimer's and control individuals. Because cell subtype variation often outweighs disease signals, I applied cell type and neuronal layer stratification to preserve true molecular signatures. Major confounders like sex, age, ApoE4, and education were controlled through SHAP explainability and stratified modeling, ensuring the model learns disease-relevant biology rather than demographic noise. This figure summarizes the full NeoPlasmaNet AI architecture. First, a biotype refiner AI agent stratifies the data by neuron layers, microglia, astrocytes, and blood cells, reducing confounding bias so the model learns biology, not population imbalance. Second, graph neural network models each gene as a node, with edges representing co-expression and pathway interactions between brain and blood genes. Third, the model uses reinforcement learning guided by neurological knowledge. It rewards itself when its predictions align with known Alzheimer's pathways, such as inflammation, calcium signaling, and oxidative stress, using cosine similarity reward to speed up convergence. Fourth, through iterative reinforcement learning across 100 epochs, the system continually improves accuracy and stability, achieving faster and more reliable learning than data-only models. Building on the architecture shown earlier, this slide illustrates how the bio-guided reward function transforms model learning from unstable to stable process. In the baseline model on the left, the orange line shows unstable reward progression, and the blue line reflects slower accuracy improvements. That's because the model relies only on raw marker gene importance scores. To overcome this, I designed a bio-guided reinforcement reward that aligns with the model's predictions with known Alzheimer's pathway gene importance vectors using cosine similarity. This means the AI is rewarded when its internal gene importance patterns mirror real biological relationships, including inflammation, calcium signaling, and oxidative stress networks. As shown on the right, this reward in orange grows steadily and their accuracy in blue converges faster, reaching optimal learning at around epoch 62 rather than 89. This slide summarizes how NeoPlasmaNet performed compared with prior models. The benchmark model from Katter and colleagues 2024 achieved about 89% accuracy using genetic data. A blood-only model trained on RNA-seq achieved 71% accuracy, while adding sex-specific brain-blood alignment with reinforcement learning improved it to 79%. The final NeoPlasmaNet model, guided by neurologically informed rewards, reached 92.03 plus or minus 0.02% accuracy and showed significant gene-level associations with p-value of less than 0.05, confirming the effectiveness of the brain-informed sex-stratified design. On the left, the plot shows how genes mutually reinforce importance during training. Immune microglia markers like TREM2, TMEM119, and C1QC consistently increased in weight, while housekeeping genes such as GAPDH declined. On the right, the GNN diagram visualizes these interactions. Each edge represents gene co-expression, and the reinforcement process highlights Alzheimer's-related molecular networks. The AI model revealed the NeoPlasma 12 gene panel, integrating both novel and established markers involved in neuroinflammation, metabolism, and oxidative stress, several of which are sex-specific due to hormonal effects. Beyond predictive accuracy, the NeoPlasmaNet discovers actionable insights that link early gene activities to modifiable risk factors. On the left, the female hormone-regulated genes such as CACNA1C and Green family members influence the brain's reward and stress circuits. These pathways connect early Alzheimer's risk with higher susceptibility to neurotoxic substances like alcohol and stimulants. This helps explain the stronger behavior component in female cohorts. In the center, several immune and infection-related genes were enriched in early-stage AD, including those responding to HPV, toxoplasma, and malaria pathways. These findings imply that preventive strategies, such as vaccination and hygiene practices, could lower infection-driven neuroinflammation risks. On the right, genes tied to taurine metabolism point toward dietary neuroprotection. Foods like scallops, clams, and seaweed are rich in taurine, which supports antioxidant defense and neuronal survival. To conclude, Neoplasma.net reimagines Alzheimer's detection as preventive and interpretable. It validated my hypothesis that blood can reflect early neuropathology and support screening for the 75% of individuals at risk who are currently unscreened. Clinically, this enables a simple blood-based test, complemented by smell and vision assessments, linked to early neurodecline. My next steps include animal model validation and collaborations to integrate this into public health screening programs. Thank you so much for listening. Please feel free to contact me at claire.78.xu@gmail.com. That is claire.78.xu@gmail.com.